Welcome to Fluid Mechanics. In this video, we'll learn about pressure and fluid statics. This topic is very important because it explains how fluids behave when they are at rest, and how pressure affects submerged surfaces, floating bodies, and manometers. We will cover four main parts: pressure and manometers, fluid forces on submerged bodies, buoyancy stability. Pressure is the normal force exerted by a fluid per unit area. You can feel pressure when you dive into a pool. The deeper you go, the stronger the pressure you feel. Pressure is a scalar quantity, which means it has magnitude but no direction. It acts equally in all directions at a point in a fluid at rest. There are three types of pressure: absolute pressure, measured from a perfect vacuum; gauge pressure, measured relative to the local atmospheric pressure; vacuum pressure, when pressure is below atmospheric pressure. Formula for absolute pressure: pressure abs, Tronder, pressure ATM plus pressure gauge. Example: if a vacuum gauge reads 40 kPa below atmospheric pressure of 100 kPa, the absolute pressure is 140-60 kPa. In a fluid at rest, pressure increases with depth due to the weight of the fluid above. The relationship is P2, char, P1, plus RGH, where R is fluid density, G is gravity, and H is the height difference. This means the deeper you go underwater, the greater the pressure. In gases, pressure change with height is very small, but in liquids, it increases linearly with depth. At the same horizontal level, the pressure in a fluid is the same at all points. We can measure pressure using several devices. Barometer measures atmospheric pressure using a column of mercury. Standard atmospheric pressure, 760 mm H, shark 1 bar 325 kPa. Manometer uses one or more fluids in a U-shaped tube to measure pressure difference. The pressure difference is calculated by RGH. Simple U-tube manometer measures gauge pressure. Inverted U-tube manometer measures pressure in gas systems. Inclined manometer gives more accurate small pressure changes. Multi-tube manometer used for complex systems. Bourdon tube and pressure transducers convert pressure into mechanical or electrical signals for modern instruments. Pascal's law states that pressure applied to a confined fluid is transmitted equally in all directions. This principle is used in hydraulic systems like car brakes and hydraulic lifts, F1A1 and F2A2. This allows a small force to lift a large weight. Example: in a hydraulic lift, a small piston area A1 can raise a large car on a larger piston A2 if the same pressure is applied to both. When a surface is submerged in a fluid, it experiences a hydrostatic force due to fluid pressure. This force acts normal, perpendicular to the surface. The total hydrostatic force on a plane surface is Fp6A, where Pc is the pressure at the centroid, and A is the area. The center of pressure is the point where this force acts. This concept is important for designing dams, tanks, and ships. When an object is submerged in a fluid, it experiences an upward force called buoyant force. This force is equal to the weight of the fluid displaced by the object. This is known as Archimedes' principle. Fb, order, RHO, fluid, GV, displaced. If the buoyant force equals the object's weight, it floats. If it's less, the object sinks. This principle explains why ships float, why balloons rise, and how submarines control depth. Stability determines whether a floating object stays upright or tips over. It depends on 2 points: center of gravity, G, point where weight acts downward; center of buoyancy, B, point where buoyant force acts upward. A floating body is stable if G is below B, or if the metacenter, M, is above G. The distance between G and M is called metacentric height, GM. A large GM means higher stability. This concept is used in ship design and floating platforms. Airplanes and submarines use pressure control for safety. Hydraulic brakes work using Pascal's law. Dams and water tanks are designed based on hydrostatic force principles. Ships and balloons depend on buoyancy and stability for operation. In summary, fluid statics helps engineers design safe and efficient systems by understanding how fluids behave when at rest.